Hello everyone, I hope you've been well on our calculus series, and I hope everything is going on so smoothly with an understanding of it. We are still on the integration technique, and today I'm going to take the partial fractions. Then the subsequent ones we are going to take integration by parts. Now partial fractions, in case you forgot what it's all about, you can go through the playlist on algebra. We treated partial fractions in there, and then you take a look at it. You already know that partial fraction evolves from rational functions or expressions, like the examples we have here. It says rational functions are mostly some p on q, where p is a polynomial, q is also a polynomial, such that a denominator is never equal to 0, because we know a number over 0 is undefined, not infinity, it is undefined. So we want to ensure that our denominator is not equal to 0, and that is a rational function. The idea of partial fraction is such that I have a complex rational function, and then I want to break it into simpler functions. This simpler function is what we term as the partial fractions. So let me help you with a quick recap of partial fraction. You know, mostly we are looking at the denominators, whether it's a linear denominator, quadratic, or repeated. So if it's linear, we know we take a over the whatever denominator we have through to the last over the denominator. If it's quadratic, we have it through to, let's say, yx plus z over whichever quadratic factor we have at the denominator. When it's repeated, you know we take it to the last term. So assume I have 2x over x plus 1 all square. Then I know I'm going to have a over x plus 1 through to b over x plus 1 squared. So if it's cubed, then I'm going to the c over x plus 1 cubed, because these are linear and repeated. And so that's a simple introduction to partial fractions. And you know what we do when we are done? We have to find the unknowns. So don't forget about that for me. So I'm done with the introduction on slide 1. That is what I got to say. So when are we using partial fractions and not substitution? Partial fraction saves our lives when mostly our integrand is a rational function. It means if I have integral and then the integrand here, you know integrand is the expression of the integral sign. This integrand is something like px over qx. But even with this, we saw substitution method which had this form. So what makes this preferable by substitutions? I'll take you through quite a number of examples, and you know when to be smart with the choice. So example 1, I want to integrate whatever function I have there, the integrand. And so let's try substitution, since you know as always I want to change the pen. It's always simple to do. So let's start with the substitution. You know I'm going to take u to be x squared minus 9. This means my du dx is 2x, which implies my dx is 1 over 2x du. Yeah. So we do our substitution now. It means integral 1 over x squared minus 9 is now going to give me integral 1 over u times 1 over 2x du. You realize there's something wrong here. Because we are moving or transforming from x to u, every x term must tend to u. But from this preamble, I could say that my x squared is equal to u plus 9. It means I can find the x term here, square root of u plus 9. This is actually plus or minus. So it means by substitution again, we have integral 1 over u times 1 over 2 plus or minus square root of u plus 9 du. Can you go ahead and integrate this thing? It becomes cumbersome. And so you have to be smart with the choice of either substitution or the other techniques we are going to go through. So we have a choice between partial and then the original substitution. So let's now use our partial derivatives. Partial fractions here, because the substitutions will make our life a bit complex to deal with. Now you know from partial fractions or rational functions, you have to determine the classification. Either it's a proper or it is improper with respect to the degree. So if it's proper, it means the degree of the numerator is strictly less than degree of the denominator. If it's improper, the degree is greater or equal to the degree of the denominator. So what is the classification here? The degree of the numerator is 1, the degree of the denominator is 2. You know this. If not, you have to go back to the algebra playlist and then go through all this. Hence it is proper. So we can easily factorize this into some 2 terms. I'm sure it's going to be x plus 3, x minus 3. Yeah, it should give us, am I right with this? Let me check my answers here. No, it can't be right if and only if this is minus. Yeah, so we have this. You realize that the denominator of interest here are linear terms, and so I can simply say this a over the first term, and then this is b over the second term. As simple as that. These are my partial forms. It is not the integral. We are just finding the partial form before we integrate. Now you have to solve for your unknowns, which I wouldn't go through in this stage. I want to assume we've all gone through partial fractions. If not, you go through the playlist for me. In finding my unknowns, a is supposed to be 1 over 6, and then b is supposed to be negative 1 on 6. This means that my integral 1 over x squared minus 9, which was given as integral now a over x plus 3 plus b over x minus 3 or dx. That's what we are doing now. So I get to now substitute my a and b. This integral 1 over, so I can bring 1 over 6 out. I think now we are smart with our integration. So this will be 1 over x plus 3 dx. If I bring the b part over, I'll have this to integrate. And what does this give us? Integration of common functions. Over here, I can now use substitution method. I can use substitution method. I know integral 1 over x is ln x, but now I have x plus 3. Okay, someone says ln x plus 3, which might be right, but then how did you get it? Is by substitution. So let me help you out here. Here is also a rational term, but it is simpler. It's not a complex rational function to use the partial. So by substitution, I can say let u equal to x plus 3, and means du is dx. If I say v equal to x minus 3, it means dv is dx. So by substitution, I have 1 over 6 integral of 1 over u, right? Dx is simply du. This is a simple rational function. Minus 1 over 6 integral 1 over v dv, and this is where the ln comes in. So 1 over 6 ln u minus 1 over 6 ln v, absolute of v. Yeah, you know, when you are done, you have to do a back substitution where your u was now x plus 3, and then your v was x minus 3, and that is the final answer plus some constants of integration. You don't forget that. So you see when to use substitution, when to use partial fractions. Substitutions will mostly go with a simple rational function, but partial fractions, partial will be okay for when you have a complex rational function. So take note of this. I think in my slide 3 I simplified further here because by algebra I could factorize 1 over 6 out and say this is ln x plus 3 over x minus 3, because the minus is the same as division. Okay, example 2. You realize that there's not a simple rational function, it's complex. Okay, so straight away I need to use partial. Is it proper or improper? The degree of the numerator is 1, degree of the denominator is 3, hence it is a proper rational function. Let me check the denominator here. I can have 1 over x. This part here is repeated linear factor. So 1 over x, sorry, a over x, b over x squared. I'm done with it. And I can take the last part as c over x plus 1. If I find the unknowns here for partial fractions, The unknown says that a is equal to 6, b is equal to -5, and then c is equal to -6. Again, if you've forgotten partial fractions, don't worry. I have the lecture videos in algebra playlist, so you kindly take a look at it. This means that our initial integral x minus 5 over here is seen complex. It's now very simple to do. It's now integral of a on x dx plus integral of b on x squared dx plus integral of c over x plus 1 dx. It looks quite simple here due to the power of partial fractions. So I can bring 6 out and say 1 over x dx, that is the a, plus if I want to have the b part, I can have -5 integral 1 over x squared dx, and then the c is -6 out, 1 over x plus 1 dx. Because they are constant, they can easily be factorized out. So I have 6, this part gives me, I don't need substitution, it's just simple in x. And then this part, I don't need substitution, it's simple. This can be written as power rule, -2 dx, okay, which is going to give you x -2 plus 1 over -2 plus 1. This gives me x -1 over -1, so 5 over x should do. Minus 6 here. This by substitution I should get ln x plus 1. You can try it out. Yeah. So this is the same as -x -1. This is -1 over x. So that's why I have it here. So I can quickly clean this aspect of the work and then try and figure this thing out. It should be ln x plus 1. Yes, I did in the first example. Alright, so I have what am I doing? Can I factorize something plus our constant of integration, because these are indefinite integral. Realize I can leave my answer in this form, or I can go ahead and factorize 6 out. I'm going to take this and then this guy again. Let me use the red. Would it even work? My red pen, where are you? I'm going to factorize this, and then that will give me x over x plus 1. Why? Because it's minus. Okay, so this is as if I have 6 out, and I have ln x minus ln x plus 1. This is what I have here. And then don't forget your other term plus c, and that is your final answer. As simple as that. Okay, I think I have 2 more examples to go, so let's take example 3. Example 3 is not a simple rational function, so I can't use substitution, but then partial fraction is here to help me out. Is it proper or improper? The degree of the numerator is 1, degree of the denominator is 2, so hence it's proper. In my last example, I'll take you through the improper form. So it's mean I'm going to have a over x plus 2, and I'm going to have b over x plus 3, because these are still linear factors. Okay, this means that my integral x over x plus 2, x plus 3 is actually equal to the integral a over x plus 2 dx plus the integral b x plus 3 dx. You have to find your b and a, which I didn't go through. From what I have here, it's as if I had a to be -2 and then I had b to be 3, and this is the same as -2 out, 1 over x plus 2 dx, and then plus 3 out, 1 over x plus 3 dx. Always go through the partial fraction for the unknowns and you'll be fine. So let's see, this is going to be by substitution method. Try it out. You should get -2 ln x plus 2, and by substitution method I should have 3 ln x plus 3. I went to the substitution method for the first one, so you can go through that for this. And what do we have here? I could have it as, by indices, this is the same as having x plus 2 to the power 2. No, because there's the negative here, and this is the same as having ln x plus 3 to the power 3. Okay, and you can simplify further if you want to, else you leave your answer just as you see it there. Okay, so enough of the proper functions. Let's take the improper rational function. Why is this improper? Because the numerator of the degree of the numerator is 4, degree of the denominator is 2. This improper. 4 over 2 is improper. And with improper, what you have to do is to use the long division. I hope you've not forgotten about that. So it means I'm going to have x squared minus 4 with a long division of this one. If you've still forgotten how to do long division, you can go to the polynomials in algebra playlist, and then you get to know how to do it. And so because I already have lecture video on this, I'll go straight and then write my solution. It's going to be s squared here. When I go through certain aspects, I'm going to get x plus 1 as the final thing. That is the remainder. So it means that p of x, q of x for long division, I know it is the quotient plus the remainder over the divisor. Okay, so the quotient I had x squared, the remainder I had x plus 1, the divisor is what I have here, x squared minus 4. Now you realize that this becomes proper. This part is constant on its own, but at this point the degree is 1, the degree is 2. It's now proper rational function. Okay, so it means that my integral of whatever I had here, the x, is actually integral of x squared dx plus integral of x plus 1 over x squared minus 4 dx. Okay, here I know I'm going to get 1 over 3x cubed. This is not derivative, it's integration. But this part I have to go to the partial fraction. What we did up here isn't partial fraction. We were just reducing it from improper to proper. And so by partial fraction, I know I can simplify this to two linear factors, a over x plus 2 and then b over x plus, I think x minus 2 should do. Yeah, this is my two partial fraction. And then you go to the same approaches as we've done up there. If you go to the partial fraction very well, equate it to the numerator here, you know, you compare certain coefficients. Should I take my time and go through this with you, or you'll be fine? You should be able to do that. We've gone through this in the algebra. So a should be equal to 1 over 4 and then b should be equal to 3 on 4. Then you can just do a substitutions. You know it's the same as 1 over 3 s cubed 1 over 4 integral 1 over x plus 2, and then the b also comes out as 3 on 4 and then whatever I have remaining. Automatically this becomes that 1 over 4, this becomes in x plus 2, you know why, and this becomes then x minus 2 by substitution. You can leave your answer this way, or you can factorize this lane aspects out, else you are good to go in this form. Okay, so let's say class text for you. It says that try and evaluate these functions. Now these are complex rational functions, so please don't even waste time using substitution method. Straight away use partial fractions. For equation 1 it is proper, equation 2 or expression 3 is also proper. You should know why. Expression 4 is improper, so it means you must go to the long division approach. I'm interested in this part of the work. Kindly do that, and then let's have our answers in the comment section. First, let's see how our partial fractions will be denoted, and when we are done, let's see the final answer. Okay, so this is how simple partial fractions are. So the most interesting aspect of our work is to apply our understanding. We are looking at the rate at which a car engine consumes fuel when the car is in motion. It says they are inversely related to the square of the speed. So the distance you cover is related to how much fuel you would need to get on track. So I have my car here, don't laugh at it. I have my fuel here. Okay. RV is given as a rate of consumption. You must always define your terms properly to know what to do. And then our V of X is the speed. You know, speed is distance over time. That's a change. And was distance given here? It says how much fuel are you going to consume. You want to find R of 1. Yeah, if you travel 1 kilometer, given that you are increasing from 3 kilometers to 5 kilometers, and someone asks, how do I solve this problem? Because we want to look at the coverage. This is an accumulation. Accumulation is not differentiation, but it's like summation along some arc time, and that is integral. So I have integral 3 to 5, and then my fuel consumption function. So the question is, are you going to use substitution or are you going to use partial fraction? Because when you look at the function for RV, it's as if I have integral 3 to 5 over v squared minus 4 dv. Are you going to use substitution method or partial fraction, and why? So let's do that and then see which one is best for our question. In the next series, we are going to take integration by part. I'm happy to say this is the last section on calculus. Stay tuned.